Hello there. It is good to share this quiet moment with you. Tonight, the cosmos feels especially close, like a vast, dark ocean just beyond the window of our thoughts. Let the gentle hush of the night settle over you. There is no urgency here, only soft space to wander. We are drifting far out tonight, past the familiar lights of our solar neighborhood, towards a world draped in a hazy, pale blue, a gas giant so distant it was once mistaken for a faint star. This planet circles the sun on its side, a strange, lonely traveler that seems to turn its back on everything, including, perhaps, its own rather peculiar name. It's a place of subtle majesty and quiet extremes, asking us to look deeper than just its surface, beyond the simple labels we give things. We'll follow the quiet mystery of this icy giant, letting the light of its distant truths settle softly in our minds. If this gentle wandering brings you peace, a small, quiet like and a soft subscribe. Help others find their way to this calm, but only when it feels truly right. For now, let your mind drift. The quiet planet is waiting, and we will begin together, unhurried and warm. Far out where the sun is, only a small, pale coin in the sky, that sideways world drifts on. It looks quiet from here, like a soft blue marble left at the edge of a vast dark floor. It is so far, so faint, that for most of human history, no one even knew it was there. And even now that we do, it still feels a little like a mistake the universe forgot to correct, a planet tipped almost onto its side, rolling more than spinning, behaving more like a dream than a proper world. If you could watch it for a long, unhurried time, you'd see how strange its motion really is. Most planets spin like a top, their equators facing the sun as they turn. Uranus does something different. Its tilt is so extreme that its poles take turns facing the sunlight. As it slowly walks through its 84-year path around the sun, one pole leans into the light for decades, while the other sits in a cold, dim twilight. Then, as the years pass, the roles slowly reverse. It is a planet of long seasons and patient changes, a world that measures time in lifetimes instead of years. When it was first found in the late 1700s, people didn't yet know about its tilt, its rings, or its icy deep interior. At that time, the very fact that it existed was already a kind of shock. For countless generations, the planets had seemed settled. Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Their paths had been traced by ancient eyes long before telescopes, their names tangled with myths and gods and old stories told under open skies. Saturn, slow and distant, was the outermost. It marked a quiet boundary in people's minds. Beyond it, there were only stars. In that world of candles and ink and hand-drawn maps, a German-born musician living in England liked to spend his nights in the garden, pointing handmade telescopes at the sky. His name was William Herschel. By day, he composed and played music. By night, he became something else, a patient watcher of the heavens. He built his instruments himself, grinding metal mirrors by hand, polishing them in dim light until they caught even the faintest glimmer from the dark. Out in the cold air, he would test and adjust them, slowly improving his view of the universe. On the night of the 13th of March 1781, Herschel was scanning the stars in the constellation Gemini. To anyone glancing up with the naked eye, the sky there looked like it always had, small points of light, steady and sharp. But through Herschel's telescope, one of those points looked a little different. It wasn't quite a pinprick. It had a tiny disk, and its edges seemed slightly soft and fuzzy. That was unusual. Stars don't show little disks. They stay sharp, no matter how much you magnify them. He didn't rush to any grand conclusion. At first, he thought it might be a comet. That was the sensible answer. Comets were known wanderers. They moved against the background of stars, sometimes slowly, sometimes dramatically, growing tails as the sun warmed their icy surfaces. So Herschel wrote down what he saw and came back the next nights. He watched and he measured. The object moved, just as a comet would, but it stayed bright and round. No tail grew, no fading haze. It simply slid through space with a steady, deliberate pace. Night after night, Herschel continued his quiet vigil. He noted the object's changing position against the fixed stars, his records growing into a trail of tiny marks on paper. Other astronomers, curious about his reports, turned their own telescopes toward the same section of sky. They saw it too, that slightly swollen point of light, drifting slowly along. They measured and calculated, using the mathematics that tied motion and gravity together, and the numbers began to whisper the truth. This object did not behave like a comet at all. Its path was almost circular, and its distance far beyond Saturn. What Herschel had found was not a chunk of ice and dust, but an entire planet, a new world, one no human had ever noticed before, even though it had been quietly orbiting for billions of years. For the first time, a planet had been added to the family not by naked eye or old stories, but by careful study and a piece of crafted glass and metal. In that moment, the solar system stretched wider in human minds. The edge, marked by Saturn, dissolved. There was something beyond, and perhaps more beyond that. Imagine him in his study, hands stained with ink and metal dust, tracing the numbers and slowly realizing what they meant. The familiar set of planets, known since ancient times, was no longer complete. The universe people thought they understood had just grown larger overnight. Astronomers began to redraw their charts. Distances were recalculated. Tables of planetary positions were updated. The neat, closed picture of the solar system opened like a door on hinges no one had known were there. Not everyone agreed at once. Some held on to the idea that it might still be a comet on a strange, distant path, but time has a way of sorting doubt. Over the following months, as the object continued its slow, steady walk through the sky, the evidence became too strong to ignore. Its orbit was regular and calm, the path of a planet held gently but firmly by the sun's gravity. The old list of 6 worlds became 7. With discovery came a new kind of problem, one that was quieter but still important. What to call this distant neighbor? Up to that point, the planets all carried names from myth. Mercury, the swift messenger; Venus, the goddess of love and beauty; Mars, the red warrior; Jupiter, the mighty king of the gods; Saturn, the ancient lord of time. These names had soaked into human language and culture for centuries. They felt timeless, as if the planets had always been called that. Now there was a newcomer, pale and remote, and it needed a name that fit into this family. Herschel, grateful for support and conscious of the world he lived in, proposed a title that had nothing to do with mythology at all. He suggested calling the planet Georgium Sidus, George's star, in honor of King George III of England. It was partly respect, partly strategy. Royal favor could keep an astronomer's work funded and his telescopes improving. Naming a planet after the king was like hanging a golden thank you in the sky. The king was pleased. Having a planet named after you is no small compliment. In Britain, some people adopted the name out of loyalty and pride. But beyond England, the reaction was cooler. French and German astronomers found the idea a bit awkward. The sky had always been a place of gods and timeless figures. To drop a human name among them, especially a contemporary ruler, felt jarring, like slipping a modern nickname into an ancient hymn. The debate spread quietly through letters, meetings, and journals. Should a new world carry the name of a mortal king, bound to a particular country and era? Or should it, like the others, be tied to the old stories that floated above borders and politics? Tradition favored the second. The planets weren't just rocks and gas. They were pieces of the sky wrapped in meaning, each name chosen to match the feeling of the world it described. As people searched for a better fit, a German astronomer named Johann Elert Bode offered a suggestion that felt simple and elegant. If Jupiter was named for the king of the gods, and Saturn for the older god who ruled before him, then the next planet outward could follow the family line. In Greek myth, the father of Saturn was Uranus, the ancient sky itself. He wasn't just another god with a throne and a story. He was the vast dome of heaven, the first great covering over the world. The idea settled gently into place. This new planet lay even farther from the sun than Saturn, cold and remote, wrapped in a blue-green mist. Naming it after the sky itself had a quiet poetry. The pattern also made sense. Jupiter, then Saturn, then Uranus, each stepping farther back into the deep roots of myth. It connected the new discovery not just to a king, but to a story older than empires, older than the languages used to describe it. At first, the name spread slowly. In Britain, loyal to Herschel and the crown, George's star lingered in use. In France, some preferred simply to call the planet Herschel, honoring the man rather than the king. For a while, the maps and writings of Europe carried a tangle of labels. But little by little, Uranus began to win. It was the only name that felt both grand and neutral, ancient and fitting. It respected tradition without tying the planet to one country or one ruler. By the early 1800s, most astronomers had accepted Uranus as the planet's true name. Herschel himself, who had hoped his royal tribute would stand, eventually let the change wash over him. The sky had chosen, in a way. It wanted its new world wrapped in the same kind of timeless myth that held the others. Of course, the story didn't quite end there. The name Uranus has carried a quieter problem of its own: pronunciation. Over the centuries, teachers and storytellers have tried all sorts of gentle twists to avoid the giggles it can bring. Some lean toward Yoor-a-noose, others toward Yoor-a-nice, and a few brave souls try to match the original Greek more closely. No matter the effort, the jokes cling to it, especially in classrooms and casual conversations. If Herschel or Bode could hear that now, they might be puzzled, maybe amused. They weren't thinking about schoolyard laughter. They were thinking about lineage and symmetry, about placing a new light in the sky where it belonged among the others. Beneath the humor, something much deeper is going on: the quiet act of naming as a form of respect. In science, naming is more than labeling. It is a way of saying, "We see you. You are real to us now." When astronomers chose Uranus, they folded this distant, icy giant into the story of the heavens. They tied it to the ancient idea of the sky itself, as if the universe were gently recognizing one of its own reflections. A god of the heavens turned into a world that circles high in that same vast space. There is a kind of grace in that. Uranus was the first planet discovered with the help of a telescope, the first found not by naked eye under open night, but by a crafted instrument and careful measurements. It belonged fully to the age of lenses, mirrors, and math. And yet, when it came time to name it, people still reached back to myth, to stories told long before anyone knew what a telescope was. The result is a planet that feels both modern and ancient at once. That mix is part of its charm. Uranus reminds us that learning more about the universe doesn't push wonder away. It invites it in. Even as we build spacecraft and write computer code to study distant worlds, we still turn to old tales and symbols to express what they mean to us. The same impulse that once imagined gods in the stars now sends machines to visit them, and yet both are moved by the same quiet curiosity. Decades after Herschel's discovery, that curiosity carried a spacecraft named Voyager 2 out to the cold edge of the solar system. In 1986, after a long journey through the dark, Voyager 2 slipped past Uranus, becoming the only visitor we've ever sent close to that sideways world. Scientists on Earth waited eagerly for its images, expecting storms and swirls like those seen on Jupiter and Neptune. Instead, the pictures showed a planet that looked almost too calm, pale, smooth, with only the faintest hints of cloud patterns. It was like looking at a frozen breath held for a very long time. But as with most things in the universe, the quiet surface hid a deeper story. Inside Uranus lies a puzzle of ice and rock and strange forms of matter wrapped in a magnetic field that doesn't behave quite like any other planets. Around it circle thin rings and small, dim moons, each one carrying its own history. And beneath that extreme tilt, scientists see the scars of a possible ancient impact, a colossal collision in the young solar system that may have knocked the planet onto its side and left it rolling around the sun like a sleeping giant. Out at the edge of sunlight, Uranus just keeps moving, slow and indifferent to the centuries ticking by on Earth. While we argue about names and laugh at syllables, it leans and turns and completes its long seasons, one after another. Yet, in its stillness, it may hold clues to a whole family of worlds, the ice giants we see in our own system, and the many similar planets now being found around distant stars. Over time, the name Uranus has become more than a word in a textbook. It is a small symbol of how curiosity stretches language and imagination to keep up with what we find. Whenever that name is spoken, there is a faint echo of the night. The solar system suddenly grew larger in human minds, and of all the distant worlds that are still waiting in the dark for their turn to be noticed and named. Seen through a telescope as a pale blue point, Uranus is not just a distant planet. It feels like a bridge. On one side stand the ancient heavens, filled with gods and stories. On the other stands the modern cosmos, measured in orbits, spectra, and data. Uranus sits quietly between them, carrying the name of the old sky god, while we study it with new instruments. Even now, in an age of calculations, the universe still lets a little mythology whisper through. Among the planets, this one seems especially fond of doing things its own way. Most worlds in our system spin like careful tops, tilted just enough to give them seasons, but still broadly upright as they circle the Sunday. Uranus is different. Its axis is tipped by about 98 degrees, so far that it is almost lying down. It doesn't simply spin, it rolls, like a marble pushed onto its side and left to turn slowly around the light at the center. Thinking of Earth makes that strangeness clearer. Our planet leans by about 23.5 degrees. That modest tilt is what gives us summer and winter, as each hemisphere takes its turn leaning toward and away from the Sunday. Mars tilts a bit more, Saturn a bit less, yet all of them keep their poles roughly pointing in the same general direction. Uranus is the odd one out the top that fell over and somehow kept spinning without ever sitting back up. No one can say with absolute certainty how this happened, but the simplest story begins in a much wilder solar system than the one we see today. Billions of years ago, when the planets were still forming, space was crowded with leftovers, huge pieces of rock and ice, some as large as moons or small planets, circling the sun on unstable paths. It was an era of crashes and close passes, surfaces melting from sudden impacts and cooling again, while gravity slowly sorted the debris into the worlds we know. In that noisy youth, something large may have crossed paths with Uranus. Not a small rock, but an ice-rich body with its own gravity and history. If it struck the young planet at just the right slant, the blow could have pushed Uranus onto its side. You can imagine two half-finished worlds drifting toward each other in slow motion, then colliding so hard that their outer layers briefly behave like liquid. Fragments are thrown out, fall back, and over time the wreckage settles into a new shape with a new orientation. Traces of such a catastrophe seem to linger in the details. Uranus's moons travel in almost the same strange tilted plane as its equator, as if they formed from debris that settled after the planet had already fallen sideways. Its magnetic field is skewed and off-center, not neatly lined up with its spin like Earth's, suggesting that the inner layers that generate it were once stirred and never fully smoothed out again. And of course there is the tilt itself, so extreme that it is hard to imagine it growing slowly and gently over time. Some astronomers have suggested another path to the same result. In their picture, Uranus might once have had a very large moon orbiting close by. Over millions of years, that moon's gravity could have tugged at the planet's rotation, slowly making it wobble and lean until it finally tipped almost all the way over. Later, the moon itself might have been torn apart by tidal forces, its fragments spreading into the faint rings and small inner satellites we see today. Whether the cause was a single violent impact or a long, quiet struggle with a vanished moon, the ending is similar. Uranus ended up sideways, and it stayed that way. That sideways stance changes nearly everything about life there, at least in theory. Because the planet is so dramatically tilted, its poles can spend decades staring almost directly at the Sunday. Uranus takes about 84 Earth years to complete one orbit, and each of its 4 seasons lasts roughly 21 of our years. For that entire time, one hemisphere drifts through a strange, almost unbroken day, while the other lies in a long, muted night. Only when the planet has rolled far enough along its path do the roles slowly reverse. Near the equator, the story is different but just as unusual. There, the sun does rise and set, yet it moves in strange arcs, sliding in at low angles through a hazy atmosphere colored by methane. Shadows stretch long and delicate, and the sky would shine in soft blue-green tones instead of the bright daylight we know. Near the poles, during their long summers, the sun would barely move, circling slowly in the same region of the sky for years. Too faint to be harsh, but too steady to ever feel like evening. From far away, it can be easy to mistake that gentleness for silence. When Voyager 2 flew past Uranus in the 1,980 seconds, the images it sent back showed a world that looked almost featureless, a smooth, pale disk with only the faintest hints of bands and storms. Compared with the swirling chaos of Jupiter or the vivid blues of Neptune, Uranus appeared almost sleepy, as if nothing much were happening there at all. But beneath that calm face lies an atmosphere that follows a very unusual rhythm. When a hemisphere finally turns away from the sun after more than 20 years of light, the pattern of heating and cooling changes. Those subtle shifts can stir the deep winds, sending fast jet streams racing around the planet and awakening storms that briefly mark the clouds with bright or dark spots. It is as if Uranus spends decades quietly storing energy, then lets it spill out in short, restless bursts before smoothing itself again. Even the invisible shield that surrounds the planet refuses to behave like the others. On Earth, the magnetic field is roughly aligned with our spin, so compass needles point toward a magnetic pole not far from the geographic one. Uranus does something stranger. Its magnetic axis is tilted by about 60 degrees relative to its rotation, and the field itself is shifted away from the planet's center. As Uranus rolls, this lopsided magnetosphere tumbles and wobbles through space, creating a protective bubble that twists and pulses in complicated ways. Many scientists see in this another quiet sign of old upheaval, frozen into the way the planet now works. For its moons, all of this makes for a very particular kind of sky. Most of them orbit in the same tilted plane as Uranus's equator, which means they too are turned side-on to the Sunday. As the planet rolls, each moon moves through its own long cycles of light and dark. You can imagine standing, if it were possible, on one of those small worlds and watching the sun crawl above the horizon only once every few decades, or glowing low in a hazy blue sky for years, before sinking again into a drawn-out dusk. Their slightly warped paths and subtle gravitational tugs are like small echoes of the ancient forces that shaped the system. It is a little humbling to realize how much can flow from a single event in deep time. One great push billions of years ago did more than knock Uranus onto its side. It reshaped its seasons, its magnetic field, the orbits of its moons, the feel of its weather, even the way we talk about it as the sideways planet, the odd one out among giants. What might have been an ordinary ice giant became a quiet outlier, rolling through the dark with a permanent lean. Time itself seems to behave differently around a world like this, not because the rules of physics change, but because the rhythms do. On Earth, we are used to quick cycles, days measured in hours, seasons in a handful of months, years that come and go many times in a lifetime. On Uranus, the same ideas stretch until they feel like something else entirely. An 84-year orbit means that a single Uranian year could last from someone's birth all the way to their old age. Because of the 98-degree tilt, that long year is divided into 4 vast seasons. When one pole tilts toward the sun, it basks in dim, steady daylight for about 21 Earth years. The opposite pole, at the same time, faces away and spends those same years in a gentle, lingering night. Only after that long span does Uranus roll far enough along its path for the lighting to slowly swap, turning day into night and night into day on a planetary scale. Along the equator, the sun rises and sets more often, but the pattern is wrapped inside this larger, slower dance. Twice during each Uranian year, there are special moments when the sun shines directly over the middle regions. These are the equinoxes, when day and night become roughly equal again, and the line between light and shadow runs neatly across the planet's face. As the sunlight skims past the thin rings during these times, the rings cast narrow, sweeping shadows over the atmosphere, like dark brushstrokes across a glowing blue canvas. Those equinoxes are rare from our point of view. They come only about once every 42 Earth years. The last time we watched one was in 2007, when telescopes caught the delicate ring shadows stretching across Uranus's disk. The next will not arrive until the late 2040 seconds. For scientists, Each of these events is a brief chance to see the planet under a very different light, to glimpse structures and motions that remain hidden during its long, tilted summers and winters. Because its orbit is so slow and our observing time so short, our understanding of Uranus is built from scattered moments. A day there, measured by its spin, is a little under 17 hours, but near the poles, that idea almost loses meaning under decades of constant day or night. Near the equator, the alternation of sunlight and darkness is real, yet it is overshadowed by the broader sweep of those 21-year seasons. If you tried to make a calendar for a moon of Uranus, you might find yourself talking less about days and more about eras of light and shadow. From that perspective, time out here feels less like a line and more like a long, slow circle. For the human mind, it would almost seem to stand still. The moons of Uranus live inside that strange rhythm. They follow the planet's tilted equatorial plane, rolling with it through its stretched-out seasons. For decades, one side of a moon may face the dim sun without a break, its ice gently lit and slowly warmed, while the other lies in a frozen night that lasts longer than many lives. Then, as Uranus continues its long journey, the light and darkness trade places, and ice that slept in shadow begins to gleam again in the pale glow. Each moon joins this slow ballet of illumination, turning and circling in step with the sideways planet. Because these cycles unfold over decades, we will never see a full one from start to finish. Our brief snapshots, one image here, one set of measurements there, can only hint at the grandeur of a place where sunrise and sunset are not moments, but eras. Changes on Uranus are glacial in spirit, not in the sense of ice creeping over continents, but in their sheer patience. The planet has waited through billions of these long seasons, rolling on its side in gentle defiance of the neat patterns around it. In a solar system that often feels like a clockwork machine, Uranus refuses to rush. It teaches, in its frozen way, that time can stretch and soften, that even in the coldest parts of space, patience can be a kind of beauty. There is no quick sweep of dawn to noon to dusk here. Light lingers, and darkness takes its time. Decades of day drift into decades of night, while the planet rolls on, unbothered by the sun's schedule. On Uranus, the sky seems in no hurry to choose between morning and evening. Beneath that slow-turning sky lies a type of planet that belongs to a rare class, an ice giant. The name sounds like something from legend, but it is a real scientific term. In our solar system, there are 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. At first glance, they might all seem alike, huge, distant spheres wrapped in clouds, but their insides tell different stories. Jupiter and Saturn are gas giants, made mostly of hydrogen and helium, the same light elements that fuel stars. Uranus and Neptune are built differently. They are smaller, denser, and made largely from substances that would freeze into solid or liquid form under normal conditions: water, ammonia, methane. These are the ice giants, worlds born from the frozen chemistry of the outer solar system. Here, the word ice does not mean snowfields and frozen lakes shining in the sunday. Inside Uranus, the pressures and temperatures are so extreme that water and other molecules behave in ways no glacier ever will. Ice, in this context, is a way of saying that these materials are trapped in dense, exotic states. Water, methane, and ammonia become thick, pressurized fluids, squeezed into phases that have no direct equivalent on Earth. Yet those strange forms dominate Uranus's mass. If you could slice the planet open in your mind, the layers would look nothing like the layers of a rocky world. On the outside is a relatively thin envelope of gas, mostly hydrogen and helium. It is only a small fraction of the total mass, but it forms the misty blue atmosphere we see. Beneath this airy shell lies a vast mantle of water, ammonia, and methane. In those compressed, hot, fluid states, our ices under crushing pressure. Deeper still, at the center, there is thought to be a compact core of rock and metal, held at temperatures and pressures where solid and liquid become slippery words. There is no sharp surface where atmosphere ends and interior begins. The outer gas wraps gradually into the icy mantle, and down you would go, meeting thicker and heavier layers with each kilometer. A descent into Uranus would never offer a firm landing. You would pass from thin air into deep cloud, then into dense, slushy materials, all while the pressure climbed to millions of times what we feel at sea level, and the temperature rose far beyond anything survivable. And yet, with all that heat locked away inside, Uranus is astonishingly cold on the outside. Its upper clouds hover around -224 degrees Celsius, making it, as far as we have measured, the coldest planet in the solar system. It even orbits closer to the Sun than Neptune, yet Neptune's atmosphere is warmer. That contrast is one of Uranus's quiet puzzles. Most giant planets glow gently in infrared light, releasing more energy than they take in from the sunday. They are still cooling from their births, letting go of the heat left over from the time when they formed. Jupiter and Saturn both radiate strongly. Even Neptune, far out in the dark, emits nearly twice as much energy as it receives. Uranus is different. It gives off almost no extra heat at all. From what we can tell, it simply reflects the sunlight that reaches it, keeping its inner warmth to itself. Why this is so remains an open question. One idea is that the same ancient impact that tilted the planet also scrambled its interior, creating layers that trap heat instead of letting it rise. Another suggests that its particular mix of materials may carry energy in unusual ways, hiding it deep below. It is also possible that Uranus lost much of its leftover heat long ago and has been coasting in the cold ever since. Whatever the reason, the effect is the same. A planet that seems frozen not only in temperature, but in temperament, still and self-contained. To peek into that hidden world, scientists compress tiny samples of water and ammonia in the laboratory, using diamond anvils and powerful lasers. Under pressures millions of times higher than Earth's atmosphere, water stops acting like any familiar liquid or solid. It becomes something in between, a phase called supionic water. In this state, oxygen atoms sit in a kind of crystal framework, while hydrogen ions move freely through it, almost like an electric current flowing through metal. If supionic water exists in the mantles of Uranus and Neptune, it could help explain their odd magnetic fields and internal layering. In that picture, the heart of Uranus would be wrapped in a restless ocean of conductive ice, alive with currents and energy beneath its calm exterior. On the outside, Uranus appears subdued, a pale disk with only the faintest markings, but deep inside, materials are being squeezed into exotic forms, possibly crackling with electrical activity. The planet is both motionless and dynamic, serene clouds drifting above, complex physics unfolding below. Even the simple gases of its upper air, hydrogen, helium, and a touch of methane, tell a gentle story. Methane absorbs red light, leaving the reflected sunlight tinted in blue and green. it can condense into tiny crystals high in the atmosphere, forming faint, icy clouds that drift through layers of gas, growing darker and denser with depth. Below the visible clouds, the atmosphere thickens into an ever heavier fog, then into a deep slushy mixture of water, ammonia, and methane. Under pressures of millions of atmospheres, these materials lose the boundaries we are used to. Ice flows like a liquid. Liquids take on rigid structures. Somewhere, far below, surrounding the core, may lie that superionic layer, neither truly solid nor truly liquid, but something in between, humming with hidden currents. From above, almost none of this turmoil is obvious. Without much internal heat to stir it, Uranus's outer atmosphere often looks still. Its cloud bands are faint. Its storms, when they appear, are usually subtle compared with the dramatic tempests of Jupiter or Saturn. The colors fade softly into one another, and even the occasional bright spots caught by telescopes seem to come and go with little fanfare. It is as if most of the turbulence has gone inward, hidden beneath a mask of calm turquoise light. In many ways, Uranus sits at a boundary in our understanding of planets. It is halfway between the gas giants and the rocky worlds, a place where materials refuse to behave in familiar ways. It reminds us that rock, gas, and ice are not fixed categories, but convenient names for how substances act under the gentle conditions of Earth. In the crushing depths of an ice giant, those categories blur. So far, much of what we know about Uranus's interior comes from indirect clues. How its gravity tugs on spacecraft, how its magnetic field tilts and bends, how much it weighs, and how big it is. We have never dropped a probe into its atmosphere or lingered in orbit to watch its weather change year after year. Apart from one brief flyby, we have only seen it from afar. Yet even at that distance, we can sense its personality, a sideways, frozen giant, turning slowly through the dark, keeping most of its secrets buried. Those secrets are written most clearly in its magnetism. Usually, planetary magnetic fields rise from deep within a core and line up, more or less, with the spin of the world they protect. Earth's field is like a slightly tilted bar magnet. Jupiter's, though enormous, is similarly ordered. Uranus does not follow that pattern. When Voyager 2 flew past, scientists expected a field centered in the planet and tipped by a modest angle. Instead, the data told a stranger story. Uranus's magnetic field is offset from the planet's center by a large fraction of its radius and tilted by nearly 60 degrees relative to its axis of rotation. The poles of the field are far from the geographic poles, and the field lines do not arrange themselves in neat symmetry. As Uranus rolls along its orbit, this crooked magnetosphere tumbles and twists. You can picture holding a flashlight that is both off-center and tilted, then spinning while you walk in a circle. The beam would sweep in complicated paths, sometimes pointing outward, sometimes sideways, sometimes curling back around. Uranus's magnetic field behaves in a similar way as it interacts with the stream of charged particles blowing from the sunday. The source of this odd field likely lies in that slushy, high-pressure mantle rather than in a small metallic core. Deep inside, conductive materials such as superionic water may be moving in uneven patterns, generating a dynamo that is lopsided and off-center. It is as if the planet built its magnetic engine in the wrong place and at the wrong angle, then simply let it run. For any charged particles or passing spacecraft, this creates a magnetic environment unlike any other. As Uranus spins once every 17 hours, lying on its side, the magnetosphere effectively reorients itself. Regions that were sheltered from the solar wind can become exposed, and areas that were open can close. The long magnetic tail stretching away from the sun may twist into a corkscrew shape, spiraling through space instead of flowing smoothly downstream. Even the auroras, the glowing curtains of light created when charged particles strike a planet's atmosphere, reflect this strangeness. On Earth, they cluster near the magnetic poles, giving us familiar northern and southern lights. On Uranus, where the magnetic poles are far from the geographic ones, auroras can appear in unusual places, sometimes at latitudes closer to the equator. They are faint and mostly detectable only in ultraviolet light by sensitive telescopes, but they are there, quiet traces of a magnetic field that doesn't follow the usual pattern. For the people who study planetary magnetism, Uranus is a quiet riddle, wrapped in blue-green light. Its field breaks the simple rule that a dynamo should sit near a planet's center and align, more or less, with its rotation. In this case, the generator likely lies in layers of conductive ices under enormous pressure, rather than in a compact core of molten metal. Deep inside that tilted world, electricity moves through unfamiliar materials, and the outcome is a magnetic field that is crooked in geometry, yet remarkably steady in overall strength. No one has watched that dynamo directly, but there are gentle theories. One picture imagines the mantle as a stack of different fluid layers. Each layer, made of conductive ices, contributes its own piece of the overall field. If those layers sit off-center or aren't perfectly aligned, their magnetic patterns would add together in a skewed way, shifting the field's center and tilting its axis. From outside, it would look exactly as we see, offset, angled, and asymmetrical, yet persistent through time. Another idea reaches back to the same ancient impact that may have knocked Uranus onto its side. A collision powerful enough to tilt an entire planet could also scramble the interior, bending and twisting the region where the magnetic field is born. If that internal symmetry was shattered early on and never fully recovered, then the magnetism we see today is like an invisible scar from that moment, a memory written not in craters, but in field lines. Odd as it is, Uranus's field is not weak. Its average strength near the cloud tops is similar to Earth's, only stretched into a much larger space. The solar wind pushes against it, shaping a magnetic bubble around the planet and drawing out a long tail that trails away from the Sunday. Voyager 2 flew through that region and found that the tail did not simply point straight back like a windsock. Instead, it twisted into a loose helix, curling millions of kilometers into space as Uranus rolled. It was as if the planet's wake were a transparent ribbon, writhing slowly in the deep, thin wind of charged particles. There's something quietly fitting about that. This is the planet that spins sideways, whose seasons last for decades, whose interior might be filled with glowing, exotic ice. Of course, its invisible forces would lean and tumble too. Where other worlds hold their magnetic poles more or less steady, Uranus lets its field wobble, flip, and spiral in time with its tilted rotation. If you could see that field with your own eyes, it might look like a vast, shimmering cocoon, warped and breathing as the planet turns. Faint auroras flaring in unusual places where particles slide down twisted lines and brush the atmosphere. The more closely scientists look, the less Uranus's magnetism resembles a tidy diagram, and the more it feels like a living system. Not random, but complex, shaped by movement, by tilt, by layers sliding past one another in the dark. It's a soft reminder that even in physics, symmetry is not a rule, only a preference. Nature makes room for the eccentric, and so Uranus keeps rolling, carrying its skewed magnetic heart inside, field lines looping and spiraling quietly around it as it circles the Sunday. From far away, none of this is obvious. At first glance, through a telescope, Uranus looks like a world with almost nothing to say. It appears as a nearly perfect disk of pale turquoise, smooth and uniform, with no bold bands like Jupiter, no dramatic spots, no obvious storms. Early observers described it as strangely featureless, like a painted glass marble hung against the night. Even with modern instruments, the sharp gaze of Hubble, the eye of Voyager 2 passing close by the planet, seems reserved. For long stretches of time, it has been, by many measures, the quietest atmosphere in the solar system. That stillness can fool you into thinking the world itself is simple, but it isn't. The calm surface is a skin stretched over deep physics and delicate balances. To understand that quiet, you have to think about energy, and especially about how little Uranus seems to have to spare. Every planet glows faintly in infrared, radiating heat back into space. Part of that warmth comes from the sun, but part comes from within, the leftover energy from a world's violent birth, slowly leaking out over billions of years. Jupiter and Saturn both shine with internal heat, still gently shrinking under their own gravity, still letting stored energy pour into their skies. Neptune, too, releases nearly twice as much power as it receives from sunlight, as if a slow, hidden furnace still burns inside. Uranus is different. As far as we can measure, it radiates almost exactly the same amount of energy that it absorbs from the distant Sunday. If there is extra heat coming from its interior, it is too faint for us to see. Whatever warmth it once held seems to have been lost long ago or locked away. The result is an atmosphere so close to thermal balance that large-scale motion is muted. There is just enough energy to keep the clouds drifting, not enough to whip them into chaos. Why this world ended up so thermally quiet is still an open question. Perhaps the ancient collision that tipped Uranus also rearranged its interior in a way that trapped heat deep below, wrapped in insulating layers that prevent it from rising. Perhaps the planet formed slightly differently from Neptune, venting most of its internal energy early and then settling into a long, cold calm. We don't yet know which story is true. We only see the outcome, a giant planet that is cold even by outer solar system standards. At the tops of its clouds, temperatures drop to around -224 degrees Celsius, close to the minimum you would expect for a planet that far from the Sunday. The air is mostly hydrogen and helium, with a sprinkle of methane that makes all the difference to our eyes. Methane absorbs red light and lets blue and green pass through, so the sunlight that bounces back from Uranus comes tinted in that soft turquoise we recognize. High above, in the thin upper layers, methane can condense into tiny ice crystals, forming faint, delicate clouds that slide through a haze almost too subtle to see. For the most part, those clouds move slowly and leave little trace. Yet the atmosphere is not entirely asleep. Every now and then, bright spots appear, towers of methane ice, rising higher than the surrounding layers, catching the pale sunlight. These storms tend to show up more often around the rare times when Uranus's seasons shift, near its equinoxes, when the sun's light begins to favor one hemisphere less and the other a bit more. That gentle adjustment in heating may be enough to stir deeper currents, briefly waking the planet's weather from its long doze. When Voyager 2 flew past in 1986, It caught Uranus during one of its quieter moods. The spacecraft's cameras strained to find contrast in the clouds, and most of what they saw looked flat. Image processors had to enhance the pictures heavily to tease out faint bands and tiny features. Compared with the swirling belts of Jupiter and the dark storms of Neptune, Uranus looked like an almost featureless orb, serene and strangely self-contained. Only later, with more sensitive telescopes and instruments that could see heat as well as light, did we start to notice subtle structures, narrow jet streams, soft temperature gradients, cloud bands that only emerge under certain lighting. These patterns hint at an atmosphere that does move and flow, but with restraint. Winds can still reach hundreds of kilometers per hour, yet, in the context of an ice giant, they are modest. The planet seems to favor smooth transitions over sharp ones, fine lines over bold swirls. In its own way, Uranus has become a kind of reference point for balance. With too much internal heat, a giant planet seethes with storms. With too little, its skies might collapse into a bland, featureless fog. Uranus sits somewhere between those extremes. Its weather is geometry more than drama. Faint stripes, soft gradients, occasional dots of brighter haze. It's as if nature decided to see how quiet a world could become and still remain alive. That quiet makes Uranus both beautiful and difficult to study. A lack of strong features means fewer clues about the depths below. Storms that might reveal circulation patterns appear rarely and fade quickly. The rings are faint, the moons small and dim. Everything about the system whispers rather than shouts. After the turbulence of its youth and the violence of whatever tipped it, the planet seems to have settled into a long, calm exhale. From afar, that calm can feel almost meditative. If you could drift in the upper atmosphere, the sunlight would be about 70 times dimmer than on Earth, a soft glow filtering through the haze. The sky around you would be a delicate blue-green, with only the subtlest streaks of cloud. Winds would murmur rather than roar. Beneath your invisible path, layers of hydrogen and exotic ices would move in deep, slow currents, taking years or centuries to complete their loops. No flashes of lightning, no rolling thunder, just the quiet, continuous shuffling of gases under gravity's gentle pull. Seen through a telescope's eyepiece, this translates into a steady, unblinking light. Jupiter flares with contrast. Saturn's rings gleam with sharp brilliance. Neptune sometimes surprises with bright storms. Uranus simply glows, a constant turquoise point against the dark, as if it refuses to flicker. It sits near the edge of the sun's reach, a still point in a universe that rarely pauses. Scientists sometimes describe Uranus as being close to thermal equilibrium, but there's a softer meaning in that idea too. Here is a planet that does not blaze with internal fire or collapse into frozen silence. It hangs in a kind of middle ground, calm and self-consistent. Its quiet is not emptiness, it is balance. All the forces that could have torn it into turmoil, now held in a careful, understated peace. Stillness, here, is not the absence of motion, but the harmony of many motions canceling each other out. For a long time, people imagined Uranus as a bare, unadorned world, just a smooth turquoise globe rolling along, with nothing much around it. Saturn's grand rings had captured our imagination so completely that it seemed almost greedy to expect another planet to wear similar ornaments. Yet Uranus, in its own shy way, has them too. The revelation came in 1977, almost by chance. Astronomers had set up telescopes in South America and Australia to watch Uranus pass in front of a distant star, an event called a stellar occultation. The plan was simple. As the planet crossed the star's line of sight, the starlight would dim once, then return, allowing a more precise measurement of Uranus's size. They watched the starlight carefully, recording its brightness moment by moment. What they saw was not a single clean dip, but a series of tiny, repeated flickers. The star blinked several times before the planet fully covered it, and then several times again after. Each dimming lasted only seconds, but the pattern was too precise to be an accident. Something thin and dark, circling Uranus, was blocking the starlight in narrow bands. Within hours, the realization spread. Uranus had rings. They were nothing like Saturn's bright, wide structures. These rings were narrow, dark, and quiet, composed of material that reflected very little sunlight. Later observations and the Voyager flyby would show that there are 13 known rings in all, from the relatively bright and narrow Epsilon ring to faint sheets of dust that barely stand out from the background. The particles in them are likely water ice coated with dark material, radiation-processed organics, and dust that have turned the ice nearly black. Because they are so dark and thin, the rings are difficult to see directly. Through a telescope, they often vanish into the planet's glare unless the lighting is just right. Much of what we know about them comes from the way they dim starlight, or from the rare moments when the sun's angle makes them stand out in silhouette. Each ring is astonishingly slender. Some are only a few kilometers wide, with edges that are surprisingly sharp. That crispness hints at a kind of gentle discipline at work. Tiny moons, shepherd moons, orbit nearby, their gravity quietly tuning the flow of ring particles. As those moons move, they tug on grains of ice and dust, pulling wandering material back toward the narrow belts. Without such caretakers, the rings would gradually spread and blur into a faint, featureless haze. When Voyager 2 arrived at Uranus, it finally gave us direct images of these structures. Against the dim blue glow, the rings appeared as thin arcs, almost like charcoal scratches wrapped around the planet. Unlike Saturn's broad, continuous bands, they seemed sparse and segmented. Some rings were brighter on one side than the other, hinting that their particles might be clumped unevenly or shaped by subtle gravitational resonances. The whole system looked delicate, almost fragile, as if a small disturbance could rearrange it. The rings of Uranus don't shout for attention, they murmur, and their beauty is easy to miss. Because the planet lies so far on its side, the rings share that same 98-degree tilt. As Uranus moves along its long path around the Sun, there are rare times, about once every 42 Earth years, when we see the rings almost perfectly edge on from here. In those short intervals, they seem to fade away, as if erased, and only faint shadows, like hair-thin lines across Uranus's upper atmosphere, reveal their presence. Later, when sunlight strikes them more directly again, they return to view, a subtle reappearance after years spent half-hidden. Their darkness tells its own quiet story. Fresh ice in space gleams. It scatters light like snow. The ring particles around Uranus do not. Over millions of years, tiny impacts and constant radiation have baked and battered their surfaces. Grain by grain, their outer layers have been altered, turned from bright ice into something darker, coated with carbon-rich dust and chemical scars. The result is a set of rings that swallow most of the light that touches them, subtle, subdued, quietly old in character, even if, by cosmic standards, they may be only a few 100 million years young. Many scientists think these rings were born from violence, A moon, or perhaps several small moons, may once have drifted too close to Uranus, crossing a line where gravity could no longer hold them together. Torn apart, their fragments spread into narrow belts of debris. Over time, collisions ground the pieces smaller and smaller into chips, boulders, and powder. The tiny shepherd moons we see today may be the survivors of that catastrophe, the last solid cores of those original worlds, still tending the fragments they left behind. Out in the dark, the rings are more than decoration. They are little laboratories of motion. Each narrow band is a compromise between gravity, collisions, and sunlight, particles bumping, clumping, drifting, and then being drawn back into line by the pull of nearby moons. The whole system works like a slow, silent clock, every orbit tuned to the next. By watching how the rings behave, scientists learn about the physics that shapes all kinds of disks, from the dusty swirls that form planets around young stars to the great flat spirals of galaxies. For all their restraint, the rings are not frozen in behavior. Sometimes an arc brightens unexpectedly, or a clump appears and then dissolves again. These small changes may come from unseen moonlets tugging on the particles, or from tiny meteoroids slamming into the rings and briefly lifting dust into view. Even here, where everything looks so quiet, the system listens to the gentle rhythm of impacts and gravity and answers with subtle, shifting patterns. If you could somehow drift among the rings, they would not glitter like Saturn's icy paths. Instead, they would stretch around you as dim plains of dark fragments, from dust-sized grains to chunks as large as a room. The sunlight, already weak at Uranus's distance, would be reflected in muted gray flashes, not in bright sparks. Above you, filling much of the sky, Uranus would hang like a huge turquoise lantern, its glow soft and steady. The loudest sound would be the one your mind imagines, the faint, constant whisper of countless particles tapping gently against one another as they share the same orbit. Because the whole system is tilted so extremely, the shadows of the rings paint strange markings across the planet. Around equinox, when the sun shines sideways into the ring plane, those thin bands cast long, straight shadows over the cloud tops, turning the atmosphere into a kind of giant sundial. For a little while, the rings don't just circle Uranus, they write on it, tracing time on a world where a single season lasts 21 years. Modern telescopes have revealed that the ring system is more layered than we first thought. Beyond the main group, known since the 1970 seconds, there are very faint outer rings made of dust, almost invisible, except when they scatter light at just the right angle. Two of them appear unusually blue, hinting at a higher content of fine, clean ice grains that somehow resist darkening. Together, all these structures suggest that the rings of Uranus are still evolving, gaining material, losing it, reshaping themselves in ways we are only beginning to glimpse. There's something very human in the way they draw us in. They do not blaze across the sky demanding notice. They wait. Saturn's rings are an obvious spectacle. Uranus's must be sought out and studied patiently before they reveal their subtler beauty. In that, they mirror the planet itself, modest, reserved, and quietly rich in detail. Around this sideways world, a family of moons adds its own gentle drama. So far, 27 have been found, each tracing a path in the same tilted plane that Uranus spins in. It is a strange sight to imagine, a planet rolling along its orbit like a wheel, and a cluster of moons circling around its sides rather than its top and bottom, all of them sharing that same 98-degree lean. Their names follow a different tradition from most of the solar system. Instead of gods from old mythologies, the moons of Uranus carry names from plays and poems. Almost all are drawn from the works of William Shakespeare, with a few borrowed from Alexander Pope. The idea came from John Herschel, son of William Herschel, who discovered the planet itself. Perhaps he felt that this distant, sideways world was better suited to kings and queens of fairy courts, lovers, jesters, and dreamers than to another row of Roman deities. It is a gentle touch, Uranus, the sky god, surrounded by actors in an endless play. Among these moons, 5 stand out as the main characters: Titania, Oberon, Ariel, Umbriel, and Miranda. They are the largest, the ones big enough to hold on to their own stories of geology and change. The rest are smaller, irregular companions, some crumpled like captured asteroids, others serving as ring shepherds or quiet fillers of space between the main orbits. Titania, the largest, is roughly half the size of our moon. It is bright by Uranian standards, its icy crust reflecting the distant sunlight with a soft sheen. Voyager 2 revealed enormous canyons and fault lines slicing across its surface, signs that the moon once swelled and cracked, perhaps as an internal ocean froze and expanded. Those great valleys, hundreds of kilometers long, are frozen evidence that Titania was not always as still as it seems now. Just beyond Titania orbits Oberon, its darker and older partner. Oberon's face is heavily cratered, a record of countless impacts over billions of years. Some of those craters have bright rims and floors, where impacts seem to have dredged up fresher ice from below, leaving pale rings against a shadowed background. The overall effect is of a world steeped in time, a moon that has changed very little since the early days of the solar system, circling quietly at the edge of its tilted realm. Closer in lie Ariel and Umbriel, 2 moons that seem to show opposite moods. Ariel is relatively bright and looks geologically younger. Its surface is carved by long canyons, ridges, and smooth plains that suggest stretching, faulting, and perhaps flows of icy material in the past. Some scientists think Ariel once experienced cryovolcanism eruptions not of hot rock, but of cold mixtures of water, ammonia, and other ices that oozed across the surface and then froze. Voyager's brief pass in 1986 caught glimpses of this complex world, hinting at a history of movement that has since grown quiet. Umbriel, by contrast, is dark and brooding. It reflects very little sunlight, making it one of the gloomiest large moons we know. Its surface is old and heavily cratered, coated with darker material that may have been laid down over eons by dust and radiation. One feature stands out: a bright ring inside a crater near its north pole, nicknamed the Cheerio. That pale patch against the dark landscape remains something of a mystery, giving Umbriel the look of a shadowed face with a single highlighted eye. And then there is Miranda, the smallest of the 5 and perhaps the strangest, only about 500 kilometers across. It would barely register as a world in many other systems. Yet its surface is a puzzle box of mismatched terrains, great cliffs, ridged plateaus, and patchwork regions that look stitched together. One canyon wall, known as Verona Rupees, drops for about 20 kilometers, making it the tallest known cliff in the solar system. In Miranda's low gravity, a fall from its top would take more than 10 minutes before you reach the bottom. Miranda looks as though it has been broken apart and put back together more than once. One idea is that it was shattered by a colossal impact and later reassembled by its own gravity. leaving blocks of crust in new, mismatched positions. Another possibility is that internal heating once softened parts of the moon, allowing sections of the surface to sink, rise, and refreeze into strange patterns. Whatever the cause, Miranda's face is a mosaic of frozen upheaval. Beyond these main moons, a swarm of smaller satellites fills in the spaces. Innermost are tiny worlds like Cordelia and Ophelia, the shepherd moons that help corral the narrow rings. A bit farther out, moons such as Puck, Portia, Rosalind, and Belinda circle in tighter orbits, their modest sizes and irregular shapes making them more like large chunks of ice rock rubble than fully rounded worlds. Their literary names add a gentle charm to the system's science, wrapped in a thin layer of theater. Farther still, beyond the paths of the Big Five, are the distant, irregular moons. Their orbits are stretched and tilted, some even moving backward compared to Uranus's spin. These small, dark bodies are likely captured visitors, once free-floating asteroids or fragments of larger objects that wandered too close and were caught. They complete the family, giving Uranus a mix of homegrown moons and adopted ones. Because the planet itself is tipped over, all of the inner moons share that peculiar geometry. They orbit in the equatorial plane, which for Uranus means circling around a world lying on its side. From high above the solar system, you would see them rolling with the planet, like tiny beads embedded in a sideways wheel. As Uranus moves through its 84-year orbit, its moons follow it in and out of long eras of light and dark. For about half that time, one pole of the planet and the moons near it faces the sun in continuous daylight, while the other hides in deep shadow. Later, the roles reverse and the slow seasons shift. Near equinox, when the sun shines along the equatorial plane instead of over a pole, the entire system briefly lines up in a flatter, more familiar way. The moons move through a shared sheet of light, and their shadows can sweep across Uranus's cloud tops in parallel tracks. Sometimes they pass in front of each other or cast tiny eclipses on the atmosphere. These alignments are rare, appearing only twice in each long Uranian year, but in those moments the sideways system reveals a hint of hidden symmetry before tilting back into its usual pose. What the moons are made of helps trace their history. The larger ones seem to be mixtures of rock and water ice in roughly equal amounts, consistent with having formed from the same disk of material that built Uranus itself. Their low densities and old surfaces carry marks from both impacts and internal shifts. The smaller, darker moons on the outskirts likely have different stories, captured pieces of the early solar system, drawn into Uranus's influence long after the main system took shape. Together, they create a layered, complicated family, some native, some adopted, all bound to the same tilted world. Voyager 2's fleeting flyby remains our only close look at this remote cast. The images it sent home of bright canyons on Ariel, dark plains on Umbriel, fractured ice on Titania, and the wild patchwork of Miranda still holds scientists' attention decades later. Since then, telescopes on and above Earth have refined our measurements and hinted at more subtle variations in motion. Hints that some of the larger moons might even hide deep subsurface oceans, warmed by small amounts of internal heat and the flexing pull of Uranus's gravity. If such seas exist, they would be cold and dark but chemically interesting, tiny laboratories for complex molecules in a place that feels almost beyond reach. Taken together, the moons of Uranus are a portrait of quiet endurance. They have circled their sideways planet for billions of years, rolling with it through long seasons, sharing its imbalance and its rhythm of extended day and night. Their orbits are not the crisp ticks of a clock, but the steps of a slow, graceful dance around a turquoise partner that itself spins against the usual grain. Among them all, Miranda lingers in the mind the longest, small, haunting, and utterly strange. It seems almost too dramatic for such a quiet system. When Voyager 2 flew past in 1986 and finally turned its cameras toward this little moon, the pictures that came back surprised everyone. Instead of a simple, cratered sphere, they showed something that looked broken, rearranged, and stitched together. Miranda looks like a moon that tried to remember itself and didn't quite succeed. Vast cliffs rise above plains of ice. Ridges and grooves cross one another at difficult angles, and nothing seems to settle into a single pattern. It's as if the surface was shattered into pieces and then gently pressed back together by a patient hand that couldn't quite recall where each fragment belonged. The first impression, when you trace its landscapes, is mismatch. Regions don't fade into each other the way they do on many other worlds. They collide. Old, heavily cratered terrains sit right next to younger stretches of smooth ice and long parallel grooves. Some areas speak of billions of years of impacts. Others look freshly worked, as though something under the crust recently stirred, rose, and froze again. Frozen plains meet jagged ridges, and the whole moon feels caught between past and present. Miranda's canyons are among its most dramatic features. The most famous, Verona Rupes, is a cliff so deep that ordinary comparisons almost fail. It drops around 20 kilometers from crest to floor, roughly 10 times the depth of the Grand Canyon. In Miranda's gentle gravity, a step off that edge would send you drifting down in silence for more than 10 minutes, through a thin, dim sky lit only by the faraway sun and the turquoise glow of Uranus. Verona Rupes is part of a network of faults and fractures that lace the moon, evidence that its crust has been pulled, broken, and rearranged on a grand scale. What could twist a tiny world into such a puzzle? Most objects Miranda's size are geologically quiet, long since cooled and frozen solid. Yet here, everything points to upheaval. Some scientists think the answer lies in tides, not of water, but of rock and ice. As Miranda orbited Uranus, its path may once have fallen into a resonant rhythm with larger moons like Ariel or Umbriel. Their combined gravity would have flexed Miranda over and over, stretching and squeezing its interior. That constant kneading could generate enough heat to melt pockets of ice beneath the surface. When the heating eased, the crust would refreeze in new shapes, ridges, valleys, and the strange oval regions seen today. Another, more dramatic story imagines that Miranda was once torn apart entirely. A massive impact, or an extreme tidal encounter with Uranus itself, might have shattered the moon into a cloud of fragments. Over time, gravity would slowly pull those pieces back together, rebuilding Miranda from its own rubble. Crustal blocks could have fallen back at odd angles, landing in the wrong places and overlapping like misaligned tiles. The result would be a world literally reassembled from memory, with mismatched terrains stitched side by side. Voyager 2's brief visit showed hints of this patchwork in the features known as coronae, huge oval-shaped structures ringed by ridges and troughs. These regions, some hundreds of kilometers across, look like giant patches sewn onto the moon's face. In one, called Arden Corona, looping faults seem to outline where a great dome of warmer material may once have risen from within and then sagged back down. Another, Elsinore Corona, shows concentric patterns like ripples frozen in mid-spread. There is nothing quite like them anywhere else in the solar system. The ridges and grooves that surround these coronae can be so intricate that scientists nicknamed the terrains quilted. It's an apt image. Miranda really does look like it's been pieced together from different fabrics, old, dark patches lying next to bright, younger ice. Craters mark the surface, but in some regions they are fewer than expected, suggesting the crust there was refreshed relatively recently on geological timescales. For a small, distant moon, that kind of youth is surprising. Up close, Miranda's landscape would feel anything but quiet. Long shadows from towering cliffs would stretch across plains of glassy ice. In the soft glow reflected from Uranus, every fracture and ridge would stand out in sharp relief. Drop an object from a height, and it would float down slowly rather than plunge, the weak gravity turning a fall into a drawn-out glide. It's a world that seems frozen in mid-movement, as if the forces that shaped it paused only moments ago, even though they have likely slept for ages. Yet for all we've learned, half of Miranda remains a secret. Voyager 2 could only photograph one hemisphere during its flyby. The other side has never been seen in detail. It may be smoother, rougher, or stranger still. Until another spacecraft visits, that hidden face will stay uncharted, its history folded away in darkness. It is humbling to know that entire landscapes, perhaps as dramatic as anything we've seen, are still waiting just beyond the edge of our vision. Miranda's orbit adds another layer to the picture. It circles close to Uranus, only a small fraction of the Earth-Moon distance away. From its surface, Uranus would dominate the sky, an enormous turquoise disk filling a good part of your horizon, casting a ghostly light across the rough ice below. Because the planet is tipped over, Miranda shares in those extreme seasons. Decades of soft daylight on one side, decades of twilight on the other, all slowly reversing as Uranus rolls along its path. Despite its fractured shell, the moon's path is steady, woven into the same sideways system as the other inner moons. Gentle tugs between them may once have fueled Miranda's internal heating, but today, they mostly keep the dance in balance. In its brokenness, Miranda tells a quiet story about resilience. Its surface is a record of shattering and repair, of energy trapped in ice and released in brief, powerful episodes. Gravity, working slowly and without hurry, took chaos and pulled it back into a globe. If you could stand on one of its icy plains and watch the faint rings of Uranus arch overhead, the silence would feel full rather than empty, full of what has already happened, of cliffs raised and plains shifted, of a world that refused to remain just a piece of rubble. From that fractured moon, it's a gentle step back to the planet that lights its sky. Seen through a telescope from Earth, Uranus glows with one of the softest colors in the solar system, a muted turquoise, like shallow seawater on a calm day. It's not the deep sapphire of Neptune or the honeyed tones of Saturn, but something in between, quiet and serene. It's easy to let that color stand in for the planet's personality, to imagine it as peaceful simply because its light feels so gentle. Behind that hue lies a simple but elegant piece of physics and chemistry. Uranus's atmosphere is mostly hydrogen and helium, but a small fraction of methane makes all the difference. When sunlight reaches the planet, it has already traveled an enormous distance and grown faint. As it passes through the upper atmosphere, methane molecules pick out certain colors to absorb, especially in the red and orange part of the spectrum. Blue and green wavelengths slip through more easily. scattering in all directions and then bouncing back into space. The light that eventually reaches our eyes is therefore filtered. The warmer tones have been sipped away, the cooler ones remain. Earth's sky is blue for a similar reason, light being scattered by air molecules. But on Uranus, methane's selective appetite makes the effect stronger and more specific. What we see is not raw sunlight, but the softened remainder after the reds and golds have been quietly removed. At first glance, Uranus and Neptune look like siblings, both distant, both icy giants wrapped in blue. Look more closely though, and the difference appears. Neptune's color is deeper, a darker blue, while Uranus is paler, with a touch of green. For years, that contrast puzzled astronomers. If both have methane-rich atmospheres, why should their shades differ? The answer seems to lie in fine details high above the clouds. Uranus appears to carry more haze in its upper layers, a thin veil of tiny particles formed when ultraviolet light from the sun breaks apart methane and allows heavier molecules to form and clump. Those small particles scatter light in a softer, more diffuse way, brightening the planet and diluting its blue into a gentler, more pastel turquoise. Neptune's atmosphere, by contrast, may be a little clearer, allowing a deeper, more saturated blue to shine through. It's a small difference in composition and structure, but it changes how an entire world looks. A slightly thicker haze here, a touch more clarity there, and one planet becomes a pale lagoon, while the other becomes a dark ocean. Beauty on a planetary scale can hinge on such delicate balances. The sunlight that paints Uranus this color is already only a faint echo of what we receive. By the time it reaches the ice giant, it is less than 1/100th of Earth's intensity. That weakened light then travels through layers of gas and haze, picking up subtle shifts in tone before reflecting away. In a sense, the glow we see is a memory of sunlight, a spectrum that has been dimmed, filtered, and recolored by distance and chemistry. Perhaps that's part of why it feels so soothing. It's light that has had a very long journey and has come back quiet. In other wavelengths, Uranus tells a more complicated story. Infrared observations reveal bands, temperature differences, and hidden cloud systems that the visible spectrum doesn't show. But in ordinary light, all of that becomes veiled by scattering and haze. The same processes that turn the planet turquoise also smooth over its details, leaving us with the impression of a nearly featureless disk. Color and concealment are, here, two sides of the same phenomenon. If you could sink gently into the atmosphere, the palette around you would change with depth. High up, the sky would glow in soft greens and blues as the last sunlight scattered through methane and haze. Deeper down, the light would dim and shift toward darker shades. Eventually, color would fade altogether into a uniform, heavy gloom, and the peaceful face seen from space would give way to the unseen churn of gases and exotic ices. From afar, though, Uranus keeps its composure. The turmoil stays hidden behind a calm sheen. To astronomers, that color is also a measurement. By studying exactly how much red light is missing and how the hue changes across the disk, they can estimate methane levels, haze thickness, and the presence of high clouds. Each shade carries information about temperature, chemistry, and altitude. A soft turquoise patch may signal different conditions than a slightly bluer band. What looks like simplicity is, in truth, a coded map. When Voyager 2 first turned its cameras toward Uranus, that delicate color was one of the things that lingered. Against the blackness of space, The planet shone like a luminous marble, simple in pattern but rich in mood. The images were taken for science, designed to measure brightness and wavelength. Yet, they captured something quietly artistic, a world painted in a single, calm tone. Over the years, better telescopes have shown that Uranus's appearance shifts with its long seasons. Slight variations in color and brightness reveal how sunlight moves from pole to pole across its tilted face. The turquoise is not a fixed mask. It breathes slowly with time. Blue, in our stories, often stands for depth, distance, and reflection, the color of deep water and open sky. On Uranus, those associations feel almost literal. It is far away, its color created by gases that formed in the cold outskirts of the young solar system. That gentle hue is a trace of where and how the planet was built, an echo of the ices that came together in darkness to form an ice giant. When you look at Uranus through a telescope, the photons that reach you have had a long path, from the sun's surface, across billions of kilometers of empty space, into a thin, cold atmosphere, through methane and haze, and back out again toward your eye. By the time they arrive, they carry not just energy, but a story about the planet that reshaped them. You are not just seeing light, you are seeing light that has learned to speak in the language of methane. In a universe of fiery reds, golden storms, and rust-colored deserts, Uranus chooses to glow softly. Its color doesn't demand attention, it invites stillness. It is the visual side of everything else the planet seems to be: tilted, distant, balanced, and quiet. And then, for a brief moment in our own history, that distant calm had a visitor. In the cold days of January 1986, a small spacecraft called Voyager 2 swept through the outer darkness and slipped past Uranus, bringing us closer to this sideways world than we had ever been before. By the time Voyager 2 reached Uranus in January 1986, it had already flown past Jupiter and Saturn, turning both from distant points into detailed worlds. After nearly a decade in flight, it was about to do the same for a third giant, becoming the first, and so far only, spacecraft ever to visit Uranus. The encounter was fast. Voyager 2 didn't slow down or enter orbit. It flew past at about 80,000 kilometers per hour, passing roughly 81,000 kilometers above the cloud tops. The period of closest approach lasted only a few hours, but the spacecraft's instruments were running almost continuously. Those few hours produced data that scientists would analyze for many years. As the probe approached, its cameras watched Uranus grow from a pale dot into a full disk. After the vivid storms of Jupiter and the intricate rings of Saturn, the first images of Uranus were striking in a different way. They showed an almost featureless globe, softly turquoise, with very little cloud contrast. Many had expected belts, spots, obvious weather. Instead, the planet looked unusually smooth and calm. Other instruments, however, showed that the world was far from simple. Voyager 2's magnetometer detected a magnetic field that was both strong and oddly configured, tilted by about 60 degrees from the rotation axis and shifted far from the planet's center. The readings confirmed what later studies would refine. Uranus's magnetic field is offset, lopsided, and tightly connected to its internal structure, rather than to a neat, central core. Measurements of temperature and composition confirmed that Uranus's atmosphere is made mainly of hydrogen and helium, with a few percent methane, the gas responsible for its color. The flyby also revealed just how cold the planet is. Cloud-top temperatures near 224 degrees Celsius made Uranus the coldest of the giant planets. even though it orbits closer to the Sun than Neptune. Infrared instruments found almost no excess heat escaping from within, unlike Jupiter, Saturn, and Neptune, which all radiate more energy than they receive. Uranus, by contrast, appeared to have a very weak internal heat source, implying a different internal history or structure. Voyager 2's cameras also captured the ring system in much greater detail than Earth-based telescopes had managed. The images showed a set of dark, narrow rings rather than broad, bright bands. 13 distinct rings were identified, many confined by small shepherd moons, whose gravity helps keep the particles in tight bands. Against the planet's glow, they appeared as thin, charcoal-like arcs, subtle but sharply bounded. As the spacecraft moved through Uranus's magnetosphere, detectors measured the behavior of charged particles trapped in the planet's field. The combination of the tilted rotation axis and offset magnetic field produced a magnetotail that twisted into a complex, corkscrew-like structure, extending millions of kilometers downstream from the Sunday. For mission planners, this meant a rapidly changing magnetic environment. For scientists, it provided direct evidence of how unusual the Uranian dynamo is. Perhaps the most visually striking results came from the moons. Before Voyager 2, only a few of Uranus's satellites had been seen as more than points of light. During the flyby, the spacecraft resolved several of them into detailed worlds. Titania showed vast canyons and fault systems, suggesting that its interior once expanded and broke the crust. Oberon appeared darker and more heavily cratered, with bright crater rims hinting at cleaner ice below a darkened surface. Ariel displayed bright, fractured terrain with long valleys and ridges that point to past tectonic and possibly cryovolcanic activity. Umbriel was revealed as a much darker, older surface, marked by craters and a few unusually bright features. Miranda, the smallest of the major moons, turned out to be the most surprising. Its surface, already described earlier, looked like a patchwork of mismatched terrains, with towering cliffs and coronae unlike anything seen elsewhere. Voyager's images turned Miranda from a faint object into one of the most geologically intriguing small bodies in the solar system. Because Voyager 2 was on a fast, one-way path to Neptune, it could only observe Uranus intensively for a short time around closest approach. After a few days of focused measurements, the spacecraft continued outward, and Uranus quickly shrank back to a dot. In total, humanity had less than a week of close-range data from the system. That brief visit, however, reshaped our understanding of the planet. Before 1986, Uranus was mostly a name, a distance, and a rough size and color. Voyager 2 revealed a sideways tilted world with unusual magnetism, a cold, low-energy atmosphere, dark rings, and a complex family of moons. The encounter also demonstrated that even a fast flyby can revolutionize knowledge, provided the instruments are well chosen and used efficiently. After Uranus, Voyager 2 went on to Neptune, setting a new record for the most distant planetary encounter. No spacecraft has returned to Uranus since. All close-up information we have still comes from that single flyby, supplemented by later observations from telescopes such as Hubble and large ground-based observatories. For decades, Uranus received less attention than Jupiter and Saturn, in part because of the difficulty of sending a mission so far. A dedicated orbiter would require a carefully timed launch, gravity assists, and a long cruise of more than 10 years. Power, communications, and operations all become more challenging at nearly 3 billion kilometers from the Sunday. In recent years, though, interest in Uranus has grown again. One major reason is that planets similar in size and mass to Uranus and Neptune appear to be common around other stars. Many of the sub-Neptune and mini-Neptune exoplanets discovered so far fall in the same general category as the ice giants in our own system, yet we have studied our two examples up close for only a few days each. To understand this very common type of planet, a detailed examination of at least one ice giant is essential. For that reason, planetary scientists have proposed a Uranus orbiter and atmospheric probe as a high priority for future exploration. The concept is straightforward in outline. Launch in the early 2030 seconds. Use gravity assists, likely including Jupiter, to reach Uranus in roughly the mid-2040 seconds. Then enter orbit and spend several years studying the system. A small probe could be released to descend into the atmosphere, measuring temperature, winds, and composition directly as it falls through the clouds. An orbiter could map the planet's gravity and magnetic fields precisely, helping to constrain the interior structure and the nature of any layered shells of exotic ices. Long-term observations would follow the development of clouds and storms over Uranus's extended seasons, observe ring dynamics over time, and repeatedly fly past the major moons to map their surfaces, measure their compositions, and search for signs of internal activity or possible subsurface oceans. Such a mission would address many of the questions left open by Voyager 2. Why is Uranus so cold compared with Neptune? How exactly is its magnetic field generated and maintained? What is the detailed structure of its interior? And do phases like superionic water play a role? How do its rings evolve and interact with shepherd moons? Do any of its moons harbor liquid layers beneath their ice? In 2022, a major planning report for planetary science recommended a Uranus orbiter and probe as the top large-class mission priority for the coming decades. If funded and launched on schedule, it would arrive when Uranus is near equinox again, a favorable geometry for studying both hemispheres, the rings, and the moons under changing sunlight. Until then, Uranus remains as Voyager 2 last saw it, distant, tilted, and relatively quiet from our point of view. The data from 1986 continue to be reanalyzed with modern techniques, yielding new details about the rings, moons, and atmosphere. But the major step forward will come only when another spacecraft makes the long journey outward, slows down, and stays. When that happens, the brief snapshot Voyager 2 gave us will turn into a long-running study of one of the most unusual planets in the solar system. For now, Uranus remains a distant target. Since Voyager 2's flyby, no spacecraft has returned. All our close-up knowledge still comes from those few days in 1986, plus years of careful work with telescopes. Future missions may change, that a dedicated orbiter and probe could arrive within a single human lifetime, but until then, Uranus continues its slow, tilted path around the Sun, largely unvisited. Out at its orbit, nearly 3 billion kilometers from the Sun, sunlight is weak. By the time light reaches Uranus, its intensity is less than 1% of what Earth receives. The Sun would appear much smaller in the sky, a bright point rather than a broad disk. Illumination there is enough to cast shadows and define day and night. But it is closer to bright twilight than to the full daylight we know. As that faint light passes through Uranus's atmosphere, it encounters methane and high-altitude hazes. Methane absorbs red wavelengths and allows blue and green light to pass and scatter, which gives the planet its characteristic turquoise color. The same process that colors the globe also affects the lighting on its moons and rings. Surfaces are lit mostly by this filtered blue-green light rather than by the full solar spectrum. Because Uranus is tilted by about 98 degrees, its relationship with sunlight is very different from Earth's. One pole can face the sun continuously for roughly 21 Earth years, while the opposite pole remains in darkness for the same length of time. Only after a quarter of its 84-year orbit does the situation begin to reverse. At lower latitudes, the sun still rises and sets, but its path across the sky is low and slanted, and seasonal changes occur on timescales measured in decades instead of months. This slow cycle means that large regions can remain in low-angle light or long twilight for a significant fraction of a human lifetime. For scientists, that extended pattern is not just a curiosity. It strongly influences how heat is absorbed, stored, and redistributed in the atmosphere and on the moon's surfaces. The way brightness changes with time and latitude carries information about atmospheric circulation and energy balance. Light is also a diagnostic tool. By measuring how Uranus reflects sunlight at different wavelengths, astronomers can infer the vertical structure of the atmosphere, the thickness of the haze, the abundance of methane, and the presence of cloud layers at various depths. When the planet approaches equinox, the sun's rays skim along the equatorial plane, and the rings cast narrow shadows across the cloud tops. Tracking those shadows helps pinpoint ring positions and refine models of their particle distribution. Near solstice, one hemisphere faces the sun for many years while the other is turned away, offering a natural laboratory for studying extreme seasonal forcing. Just beyond Uranus orbits Neptune, the other ice giant. At a glance, they look like close relatives, similar radius and mass, similar bulk composition dominated by hydrogen, helium, and ices such as water, ammonia, and methane. Both show strongly tilted, off-center magnetic fields, yet their behavior is noticeably different. Uranus is comparatively subdued. It radiates only about as much energy as it receives from the sun, indicating a weak internal heat source. Neptune, on the other hand, emits more than twice the solar energy it absorbs, suggesting a much warmer interior and active heat transport. That internal heat drives strong convection and fast winds. Neptune's atmosphere supports some of the highest measured wind speeds in the solar system and large transient storm systems. Uranus, with little detectable excess heat, shows fewer and generally weaker visible storms, especially at the time Voyager 2 flew by. Why two planets of similar size and composition evolved so differently remains an open question. One leading idea is that Uranus experienced a major collision early in its history. The same event that tilted the planet onto its side could have rearranged its interior, creating stable layers that inhibit convective heat transport. If heat cannot move easily from the deep interior to the atmosphere, the planet will cool and fade more quickly. Neptune, which shows no sign of such an extreme tilt, may have maintained a more efficient path for heat to escape. Another factor could be subtle differences in composition and formation location. If Uranus and Neptune formed at slightly different distances from the young sun, they may have incorporated different ratios of rock, ice, and gas. Those differences, though small, could affect how quickly each planet loses heat and how vigorously its interior circulates. Current models can reproduce some aspects of their behavior, but no single explanation yet accounts for all observed contrasts. Their magnetic fields add another layer of complexity. Both Uranus and Neptune have fields that are significantly tilted relative to their spin axes, and displaced from their centers. This suggests that their dynamos operate in intermediate layers of conductive ice, rather than in compact metallic cores, as is thought to be the case for Earth and Jupiter. Neptune's field, while still unusual, appears somewhat more regular in behavior. Uranus's field is more extreme in its offset and geometry, consistent with a history that may include large-scale internal disruption. Even in color, the differences are informative. Uranus appears lighter and more greenish-blue. Neptune is a deeper blue. The current best explanation is that Uranus has more high-altitude haze, which brightens and desaturates its color, while Neptune's atmosphere is clearer, allowing methane's blue absorption signature to dominate more strongly. These variations in haze thickness and atmospheric chemistry can be tested with spectroscopy and radiative transfer models. Beyond their role in our own solar system, Uranus and Neptune are important because they serve as local examples of a very common class of exoplanets. Surveys of planets around other stars show that worlds in the size range between Earth and Neptune are among the most abundant. Many are similar in size and mass to the ice giants, with thick, volatile-rich envelopes. Yet for most exoplanets, we see only coarse properties, average density, orbit, and sometimes bulk atmospheric composition. Uranus and Neptune act as calibration points. By understanding their internal structures, heat flows, magnetic fields, and atmospheric dynamics, scientists can better interpret the limited data available for distant worlds of similar size. Questions such as how efficiently planets cool, how their atmospheres mix, and how their magnetic fields are generated all have implications for exoplanet structure and evolution. In that sense, comparative studies of Uranus and Neptune link local observations to a broader picture of planetary systems. One ice giant is relatively quiet, with a weak internal heat source and a nearly featureless visible atmosphere for long periods. The other is active, with ongoing storms and strong internal flux. Together, they show how planets of similar mass can follow different evolutionary paths, depending on early events and internal processes. Future missions to either or both ice giants would refine this picture. Long-term measurements of temperature, composition, and magnetism, combined with detailed mapping of moons and rings, would help resolve many of the uncertainties that remain from the brief Voyager era. Until then, telescopes and models must do the work, drawing as much information as possible from the faint, filtered light that reaches us from the outer solar system. Uranus and Neptune are often called twins, but in many ways they are still strangers. We have only one close flyby of each, and the same spacecraft that revealed them, Voyager 2, has long since moved on. No orbiter has yet stayed to watch their seasons unfold. For now, they remain the least explored of the major planets, two large, nearby examples of a planet type that seems to be common across the galaxy, but that we barely know in detail. Future missions to Uranus, and eventually to Neptune, are expected to change that. An orbiter and atmospheric probe could measure their interiors, fields, and atmospheres far more precisely than a flyby ever could. Comparing the two ice giants, similar in size and composition, but very different in behavior, would help test ideas about how planets cool, how their layers separate, and how their magnetic fields are generated. That, in turn, would sharpen our understanding of the countless sub-Neptunes seen around other stars. Among the two, Uranus stands out most clearly because of its tilt. Its rotation axis is tipped by about 98 degrees, so the planet effectively rolls along its orbit. The simplest and most widely accepted explanation is a large impact early in its history. A body perhaps the size of Earth or larger likely struck Uranus at an oblique angle, transferring enough angular momentum to tip the planet over without destroying it. Numerical simulations show that such events are plausible during the chaotic stage of planet formation. That one event reshaped almost everything about Uranus's behavior. The extreme tilt drives its long seasons. Decades of continuous sunlight for one pole, decades of darkness for the other. It set the plane in which the regular moons and rings orbit, since they follow the planet's equatorial plane rather than the plane of its orbit around the Sunday. It may also have rearranged the interior in a way that affects the magnetic dynamo and the flow of internal heat. Physically, Uranus is still a stable planet. Its orbit around the Sun remains nearly circular and lies in the same general plane as the other worlds. Its moons follow predictable paths. Gravity keeps the system coherent. What changed is the orientation of its spin, not the basic balance of forces that hold it together. In planetary dynamics, this is an example of a system finding a new stable configuration after a disturbance, different from the default case, but not inherently less robust. The tilt also appears in the details of the magnetosphere. As discussed earlier, Uranus's magnetic field is both offset from the center and tilted significantly from the rotation axis. If the interior layers were re-stratified by the impact, the region that now conducts electricity and drives the dynamo may sit in a shell away from the center, naturally producing an off-center field. Over time, this configuration has remained stable enough to persist for billions of years, even if it looks irregular compared to Earth or Jupiter. From an observational standpoint, Uranus shows that average planets may be rare. On paper, it is similar to Neptune, radius of about 4 Earths, mass around 14-15 Earth masses, dominated by hydrogen, helium, and ices. In practice, its internal heat output, its atmospheric activity, and its axial tilt are all significantly different. A single major event in its early past likely pushed it onto a path unlike its near twin. For planetary science, this is a useful reminder that formation histories matter as much as initial conditions. The long timescales involved are also important. Uranus's orbital period is 84 Earth years. A full seasonal cycle from one orientation of the axis relative to the Sun back to the same takes that long to complete. Human missions, by contrast, operate on timescales of years to decades. A flyby only samples a narrow slice of that cycle. An orbiter, staying for many years, would be able to track how clouds, temperatures, and winds change as sunlight gradually shifts from one hemisphere to the other. Looking back, Uranus has expanded our view of the solar system at several key moments. William Herschel's discovery in 1781 showed that the planetary family extended beyond Saturn, doubling the known size of the system at the time. Voyager 2's flyby in 1986 turned a faint telescopic disk into a detailed world with rings, moons, and a complex magnetic environment. Each step revealed that the outer solar system is not a simple repetition of the inner, but a region with its own types of worlds and its own rules. Today, large telescopes continue to refine that picture. High-resolution imaging and spectroscopy allow astronomers to monitor the atmosphere, track occasional storms, and measure subtle changes in brightness as seasons advance. Radio and infrared observations help constrain the planet's temperature, structure, and composition, but there are limits to what can be done from a distance of billions of kilometers. Many key questions about the interior layering, the exact nature of the ices, and the details of the dynamo require in situ measurements. That is why Uranus now sits near the top of priority lists for future exploration. Scientifically, it offers a rare test case for extreme axial tilt and its effects on climate and magnetism, a nearby representative of the most common exoplanet size class. A natural laboratory for studying an ice-rich interior, coupled with an off-center magnetic field and a compact system of moons and rings that may even include bodies with subsurface oceans and geologically active surfaces. Technically, it is challenging, but reachable. With current propulsion and gravity assist techniques, a mission launched in the early 2030 seconds could arrive in the mid-2040 seconds near an equinox when both hemispheres and the ring plane are well lit. At that point, Uranus would become not just a distant object of study, but a place with a long-term robotic presence, a planet observed day after day instead of briefly in passing. Until such a mission flies, the picture we have will remain incomplete. Yet even in its current state, Uranus has already played an important role in broadening our sense of what planets can be. It shows that large impacts can permanently alter a world's orientation, that internal heat can be weak even in a giant planet, and that rings and moons can adapt to unusual geometries and remain dynamically stable over long periods. In the context of the solar system, Uranus marks a transition region beyond the gas giants, but inside the Kuiper belt, close enough to study, but far enough to challenge us. In the context of planetary science, it marks a conceptual boundary between theory and measurement. Many of our present ideas about its interior and history are based on models constrained by limited data. A future orbiter and probe would shift that balance toward direct observation. In that sense, Uranus is both a finished world and an unfinished chapter. The planet itself has long since settled into its tilted configuration, with its moons, rings, and fields in steady patterns. Our understanding, however, is still in an early stage. The next spacecraft to visit will not just refine details, it will likely change the overall picture again, much as Herschel's telescope and Voyager 2 once did. When that happens, Uranus will move from being the quiet outlier of the outer planets to being one of the best characterized examples of an ice giant. And the lessons learned there about tilt, heat, composition, and evolution will apply far beyond our own system to the many similar worlds that orbit stars all across the galaxy. Future plans for a Uranus orbiter and atmospheric probe build directly on these scientific priorities. The current mission concepts aim for a launch in the early 2030 seconds, an arrival in the mid-2040 seconds, and then several years in orbit around the planet. From there, the spacecraft could deploy a small probe to descend into the atmosphere, measuring temperature, winds, clouds, and composition as it falls, while the orbiter maps the gravity field, refines the structure of the magnetic field, tracks storms and hazes over changing seasons, and flies past the major moons to study their surfaces and interiors in detail. In combination, those measurements would turn many of today's models of Uranus from informed guesses into well-constrained descriptions. Until such a mission flies, Uranus remains a largely remote data point, a pale, tilted ice giant observed from afar by telescopes and remembered through a brief visit in 1986. It continues to circle the Sun every 84 years, its axis fixed in its unusual orientation, its rings and regular moons following the same sideways plane. On human timescales, not much appears to change. The long seasons, the weak sunlight, and the limited internal heat output all contribute to a picture of a planet that evolves slowly and quietly compared with the more energetic giants closer in. That apparent stillness is itself part of the science. Uranus shows what happens when a large planet reaches near equilibrium between the energy it receives and the energy it emits, when internal heat no longer dominates the atmosphere's behavior, and when an extreme axial tilt restructures climate and magnetism without disrupting overall orbital stability. It demonstrates that planetary systems can absorb major events, such as the impact that most likely caused the tilt, and still settle into long-lived configurations in which moons, rings, and fields all remain dynamically consistent. Seen in context, Uranus is neither an outlier to be ignored, nor just a curiosity at the edge of the solar system. It is a key example of a very common type of planet, an ice giant with a complex interior and an unusual geometry, sitting at a distance where processes play out over decades instead of days. Studying it in more detail would not only complete our picture of the outer planets, but also provide a crucial reference for interpreting the many Uranus-like worlds now being discovered around other stars. Until the next spacecraft arrives, the planet will keep following its slow path under faint sunlight, holding on to the details that a future mission is designed to measure directly.